गुड इवनिंग ऑल फ्रेंड्स, साइंस की दुनिया में आपका स्वागत है। आज हम डिराइव करने वाले हैं फार्मूला फॉर प्योर बेंडिंग। ये क्वेश्चंस आपके किसी भी फॉर्म्स में आ सकता है, लाइक डेरिवेशन ऑफ अ फ्लेक्चुअल फार्मूला फॉर अ प्योर बेंडिंग, डिड्यूस अ प्योर बेंडिंग फार्मूला, और डिराइव अ फार्मूला फॉर अ स्ट्रिप विच इज अंडर लोड. So suppose these strips are steady with the point of A and B, and it's applying a load with W on the metals, and it's having a length of L, and by that we are assuming that the length of these both part will be L by 2 and L by 2. By this load there will be a curve we will be creating after this bending. So this curve will be known as a bending curve, of beam. So this is a general diagram which normally shows as a bending of a strip. In actual strip, there will be a length, there will be a width, and there will be a thickness. So just we have taken a section of this strip as this one. In this we have taken section of A, B, C and D. So in this section AB and CD, there will be a neutral axis, which is interacting on point E and F. In just below E and F, there will be a effective layer which is supposed to expand, that is G and H, which is having on the distance from E and F, that the distance is Y. This is a neutral axis. What will happen if it bends? So it will be like this one. Suppose a W load is applied on this, so definitely it will deform like this. This A and B section will be going to like this one, and this C and D section will be going to like this one. So A will be A dash, B will be B dash, C will be C dash, and D will be D dash. That neutral axis will be same. E will be E dash and F will be F dash. G will be G dash and H will be H dash. This one was on the parallel, so there was a meeting on the only on the infinite, but while on the bending stress, it will be meet on the point O with angle of theta, and distance from layer and distance from O to E dash and F dash will be R, that is radius, and the distance from E dash F dash to G dash H dash will be Y as usual from this. Now come to the derivation part of this equations. So let us this is figure number 2, this is figure number 3. So the strain, that is E, is equal to the change in length upon original length. So obviously the strain will occur only in this particular area. So we will consider we will consider the strain in only this area. So that is change in length will be G dash H dash minus the original length, which is G and H, upon original length, that is also G and H. Now GH equals to EF according to the figure number 2. So E equals to G dash H dash minus EF upon EF. This is equation number 1. Now the E dash and F dash will be equals to E and F because both are on the neutral axis. So neutral axis length will not be changed. So E dash and F dash. E dash and F dash will be R theta because the length of arc equals to angle into radius. The same way G dash and H dash will be R plus Y is R plus Y, D dash and dash, this length will be equals to this. So G dash and H dash equals to R theta plus Y theta. Now we will put this all in equation number 1. So what is equation number 1? That is E equals to G dash H dash minus EF upon EF. So E equals to G dash H dash is R theta plus Y theta, R theta plus Y theta, this minus E and F. EF will be R theta upon EF will again R theta. So E equals to this R theta will be cancelled out and this theta will also be cancelled out as a numerator upon denominator, Y upon R. So as a stress will be equals to the length distance from the neutral axis upon the radius of curvature R. Now again we will go ahead with the Hooke's law. What actually Hooke's law says? It says that stress is directly proportional to strain. Means the stress is equals to the constant into the strain. In this, sigma is equal to stress, this one is strain, and capital E equals to the Young's modulus of elasticity. So according to this, E equals to the stress upon Young modulus of elasticity. So by this, this stress will be a bending stress. So obviously, so as we know from this relationship, that is strain is equal to pi upon r and E is equal to sigma b upon E. So the y upon r equals to sigma b upon E. So E upon r equals to sigma b upon y. This is equation number 2. Now sigma b, that is stress, bending stress, equals to E upon r into y. This is an equation number 3. If E, which is Young modulus of elasticity, and r, which is radius of curvature, both are in constant, then bending stress is directly proportional to the length change or a layer distance from a neutral axis. Now come to this, the cross-sectional area means this will be having a cross section. There will be a neutral axis and there will be a force acting on this particular area. This is a neutral axis. This length is obvious with the y. This area, the strip of area is dA, and the force acting from this top weight, which is equal to the dF. So now we will discuss here in a broad way. This is a neutral axis. This length is y, neutral axis, and this force is dF, and the area is also a dA. Now the force acting on the elemental strip because of bending. This will be dF equals to the bending stress into the area of strip. Why so? Because As we know, the stress equals to the force upon area. So as for the force equals to the stress into area. So according to this relation, it will be dF equals to the bending stress into the area of strip. So dF, as we know from the equation number 3, that the stress bending stress equals to the E upon R into Y into dA from equation number 3. Now after this equation, we will take a moment of force about neutral axis. What is this? This is a neutral axis. So if we will take a momentum of a force about neutral axis, so dm equals to will be a df into y, means force into length. Dm equals to, so df equals to this one, E upon R into Y into dA, again this one Y. So dm equals to E upon R into Y square into dA. If we will integrate on the both side, so integration of dm equals to E upon R constant, and Y square dA. As we know, the area into the distance square equals to the second moment of inertia, that is I. So on this place we can put I, which is again that integration of this dm will be again m, and this both are as a constant as a length and area. So as we know, the distance square into area equals to a second moment of inertia, that is I. So m upon I equals to ER. This is again a relationship with ER. Again, if we will take a relationship that ER is E upon R is equal to the bending stress upon the length equals to M upon I. So again, from equation, this equation number is 2, sorry. So M upon I equals to E upon R equals to the sigma B upon Y. This is the formula of flexural formula for pure bending, where E equals to Young's modulus, elasticity, R equals to the radius of curvature, sigma b equals to the bending stress, y equals to y is equal to the distance of layer in which bending considered. M is equal to the bending moment and I is equal to the second moment. So this is an expression we have made for a pure bending. Guys, please subscribe on my channel for more videos. Thank you.